Hi, I'm Josh Temple.
I'm Sean Hansen.
And I'm David Thompson. This is our group presentation for ECE 441X.
We'll start off with the project overview. There are many dance video games on the market today that have you stomping arrows to the beat of music according to instructions on the screen. These games usually have about 80 songs to choose from, but what if you want to dance to your own music? That's where our project comes in. Team Sandstorm intends to expand the idea of dance rhythm gaming to let players dance to any music they want to. There are no games on the market that take music as an input rather than an output, so this game will be among the first of its kind. Here we have a rough drawing of what the game will look like. It'll consist of a dance pad and an enclosure housing the user interface, microcontroller, and power supply. When the user turns the game on, they'll be able to control the menu on the LCD screen here using the dance pad. The user will start by playing any song they want through these speakers and then press start on the dance pad. Using the microphone on the enclosure, the game will record the music for 10 to 20 seconds and find the beats per minute, or BPM, of the music. When it has the BPM, the game will start. First, a randomly chosen arrow will flash green, and then that will be the user's cue to step on that arrow exactly one beat later when the arrow flashes blue. The LCD screen will tell the user whether or not they hit the arrow correctly. This process repeats until the user presses the stop button here, at which point their score will be displayed on the LCD screen. We think this will be a fun and addicting game that anybody will be able to enjoy, no matter what kind of music they like.
Hi, I'm David Thompson. I'm here to talk about 10 primary potential project requirements for our project. The first has to deal with software. The game must have software capable of beat recognition through a microphone or audio input port operating within the frequency of 20 to 20,000 Hertz and a decibel range of 20 to 90 decibels. The sensitivity rating must be negative 44 decibels plus or minus 2 decibels. The beat recognition software must be able to light up arrows within 0.1 second of the beat for 7 out of 10 user-supplied songs. The game timing must also be accurate. The game must detect if the user has stepped on an arrow within 0.2 seconds before or after the beat, and the arrow is lit up. The game must also have a user interface display that includes a menu and also indicates whether steps were hit correctly during gameplay. The game must be user-friendly. 7 out of 10 surveyed people must be able to start a game within 1 minute. The dance pad arrows must light up to at least 20 lumens in 2 different colors. The dance pad must be durable. It must be able to withstand the weight of a user weighing 300 pounds. The game must also feature 3 difficulties to choose from. The dance game must be portable, total weight of 40 pounds or less. The game case dimensions must be no greater than a 2 by 2 by 2 foot cube, and the dance pad dimensions no larger than 4 by 4 feet by 3 inches tall. The game must also be affordable, the total cost being no more than $150.
Hello, I'm Josh Temple, and I will be discussing the top-level diagram. This is the single block top-level diagram with 4 inputs and 3 outputs. The inputs being how the environment interacts with the game, how its conditions are, the power, how the user interacts with the game, and the music that it records in. As the outputs, we'll have how the game affects its environment, the display so the user knows what they're doing, and the lights to the dance pad, so it'll light up. This is the top-level diagram with all the major components shown. We will have the Atmega 128 microcontroller as the heart of our project. It will be powered by 4 1.5 volt AA batteries and regulated to be between 4.5 and 5.5 volts. From there, the microcontroller will power and control all the other interfaces, like the music detection, lighting on the dance pad itself, and the user interface. It will be pre-programmed with software that allows it to play the game, and will have an enclosure to protect it from any elements externally. And next is the Atmega 128, the heart of our project. The Atmega 128 runs off 4.5 to 5.5 volts DC. It has RISC architecture, which means it has less commands, but they're smaller and can run faster and at the same time, whereas CISC, complex instruction set computing, has a larger set of commands, but each one is bigger, takes more time, and cannot be ran at the same time. There are 4 timer counters, each one allowing several different types of interrupts. You have several interrupts running at the same time. There are 6 I/O ports on the Atmega 128 that have 8 pins for data and 2 pins for VCC and ground. Each pin has a voltage range of 0 to 5 volts DC, and each pin can source up to 20 microamps. and up to 100 microamps per the port, while the VCC and ground pins can source up to 200 microamps. Also has an LCD screen that has 2 lines of 16 digits that's programmable through port F. It also has an internal clock that runs off a crystal oscillator running at 32 kilohertz and 16 kilohertz. Here is the ATmega 128 on the PCB provided by the TechBot store. There is the LCD display that comes with it that we will not be using for this project, and the several ports that it has already included with the schematic of the whole PCB.
Now for the music detection block. Over here we have an Electret microphone. We chose to use an Electret microphone because they're small, inexpensive, and sensitive enough to record music. We chose this particular model for 4 reasons. Number 1, it's omnidirectional, meaning it can record music coming at it from any direction. Number 2, it can run on anywhere from 3 to 10 volts. Number 3, it detects frequencies from 20 to 20 kHz, which is the full range of human hearing. And finally, number 4, it has a sensitivity of negative 44 decibels, which is on the higher end for Electret microphones. So this means it will be able to pick up music even if it's played quietly. The microphone will be powered by 5 volts from the microcontroller. The microphone's impedance is 2.2 k ohms, and that in combination with this 2.2 k ohm resistor creates a voltage divider, and the signal in the middle will be able to have its maximum room to swing. Then we have a DC blocking capacitor C1, which makes sure that only the AC audio signal can get past. And then over here we have a low-pass filter. The values of the resistor and capacitor here were calculated so that only music below 160 Hz will be able to get through. This is because we only want to record the bass in the music to calculate the beats per minute. And then since the microphone only produces about 20 millivolts, this signal will need to be amplified. So we chose the LM386 power amplifier chip. It has a gain of 20 to 200, so we'll be using a gain of 20 to amplify the signal to a suitable level for the microcontroller to read it with the analog to digital converter.
Now let's talk about the user interface. Although the ATmega 128 comes with a 2-line 16-bit LCD screen, we instead opted for a different LCD screen because of its capabilities. We instead chose the LCD 20X4BL LCD screen available at futurelect.com because of its capabilities, including backlight capability, a number of characters on the screen, and the cost associated with it. This is a diagram outlining the ATmega 128 integration with the LCD screen. Some pins to note are the pins DB0 through DB7, RW, E, RS, VO, K, and A. The RS pin controls whether the data bits are read as data or as commands. The RW pin controls whether data is read or written to the LCD screen. The E pin enables the LCD. The K and A pins control the backlight, and the VO pin controls the contrast to the LCD. Now let's talk about a rough timeline for our project. This is the 2011 fall timeline based upon components and their due dates, and the corresponding timeline of those components, most of them culminating to the end of the term. This is the winter 2012 timeline and the components. This is the first set of components focusing mainly on components of the project, and the second part with components and software included. The 2 corresponding timelines are separated between software and component. In the software timeline, we work mostly upon music detection and dance track generation before finally completing the user interface and completing a full project prototype at the end of winter term. In the component timeline, we work upon a foundation of a power regulator block and microcontroller block before moving on to a dance pad, lighting block, microphone and speaker, and enclosure block. This culminates to a final prototype due at the end of winter term. This is the spring term task list and corresponding timelines that culminate at the Engineering Expo, where our project will be on display for customers to view. That concludes our presentation. Thank you for watching.